Okay yaar. Okay. Hi everyone. So good afternoon here. Good afternoon all. Good afternoon. So first of all, let me know whether audio and video everything clear here. Is audio and video everything clear? Yes or no here? Right? Okay yaar. So we'll start the session here. So good afternoon all. So we are dealing with the subject electromagnetics, right? In the previous sessions we have studied about del operator. We have started with del operator. Yes or no? We have studied del operator. So we have seen that whenever this del operator operates on scalar function, the operation is nothing but gradient. Whenever it operates on vector function, you are having two operations. One is divergence, another one is what? Another one is curl. Right? Okay. So we have seen in detail what do you mean by gradient? What do you mean by gradient? How to represent gradient mathematically, and also what is the physical interpretation of gradient. So those things we have seen. So next after that we have studied about flux here. After that we have studied about flux. Okay. So just I am revising here whatever we have studied in the previous sessions. So those things I am just revising. Okay. So next we have studied about flux through any surface. So what do you mean by flux through any surface here? The flux through any surface is a measure of what? Is a measure of how much of the given vector field is penetrating or flowing through a given surface. Penetrating through a given surface or flowing through a given surface, or you can say passing through a given surface. So how much of the given vector field is penetrating or flowing or passing through a given surface. So that is defined as what here? That is defined as flux. Yes or no? Okay. So we have defined flux here. So mathematically how to represent flux here? We have seen that the flux through any surface can be represented by double integral f bar dot what? F bar dot dA bar. So this is the general representation of flux, right? Okay. This is the general representation of flux. Next, if you want to represent the flux through any closed surface here, how to represent the flux through any closed surface can be represented by closed surface integral f bar dot what? F bar dot dA bar. So how we are representing this flux and all these things we have already discussed here. Right? Next we have seen that whenever f bar is constant with respect to this integration variables here. If f bar is constant with respect to the integration variables, then you can write directly flux as what here? F bar dot a bar. You can directly write f bar dot a bar. So if f bar is constant with respect to what? With respect to integration variables. Right. So these things we have seen here. So once we have completed flux, about flux, then we have started studying about divergence. Here, right? Divergence. So what do you mean by divergence here? So what is the physical interpretation of divergence? What I have told? Tell me what I have told. It is a measure of what? It is a measure of, just I am revising here. It is a measure of how much of the given vector field, how much of the given vector field is spreading away or leaving away or diverging away. are diverging away from a given point, diverging away from a given point. See, I said always remember this point here, that is always gradient, divergence and curl all are defined at what? All are defined at a point, all are defined at a point. So this point is very, very important here. Okay. So divergence means is nothing but what here? It is a measure of how much of the given vector field is spreading away or leaving away or diverging away from a given point, So we have taken some examples here. So just I will briefly explain those things here, what we have done in the previous session. So we have taken plus q charge, So whenever you take a positive charge, we have seen that all the field lines will be moving away from what? Away from positive charge. All the field lines will move away from positive charge in this manner, right? So if you try to determine the divergence exactly at the location of source here. So here what is present here? Plus q, that is nothing but what? That is nothing but source. So this is the source for this field. This is the source, that is plus q. Plus q is the source for what? Source for this field here. Here you are having plus q, right? So plus q is the source for this field, right? So what is happening at this location? What is happening? All the field lines are moving away from the given point. All the field lines are leaving away from the given point. So that means if you try to calculate the divergence exactly at this location, you are going to get what? You are going to get divergence not equal to 0. Since all the field lines are leaving away from this point, you are going to get divergence greater than 0. And at this location, what is present here? Source is present, right? Next what we have seen here is, next we have taken minus q here. So we have observed that all the field lines are going to converge towards what? Towards minus q, or I can say all the field lines will move towards what? Towards minus q, right, in this manner. So now here all the field lines are converging towards this minus q. Yes or no? So here the field is not diverging, but the field is what? Converging. So convergence is opposite to what? Opposite to divergence. So if you try to determine the divergence at the location of minus q, you are going to get divergence value as what here? Negative. Yes or no? Because here the field is not leaving, instead the field is converging towards this point. So convergence is opposite to what? Opposite to divergence, and hence at this location you are going to have divergence less than 0, and at this location we will get divergence not equal to 0. Since all the field lines are sinking towards this point, we will say here what is present here? At this location what is present? Sink is present. Okay, so here at this location source is present, and at this location we will say sink is present, right? Next, if you consider plus q and minus q at the same location here, plus q and minus q are placed at the same location. So in that case, the net charge here is equal to what? Net charge here is equal to 0. So if there is no charge, net charge is equal to 0, then what happens here? There will be no field surrounding this net charge. Yes or no? Because the net charge is equal to 0, and hence it is not going to produce any field lines. Right. So that means here if you try to determine divergence, what you are going to get? Here no field is either leaving from this point or converging towards this point. So in this case divergence is equal to what? Divergence is equal to 0. At this location I can say simply neither source nor sink is present. Neither source nor sink is present. Neither source or sink is present at this point. See, actually speaking, here you are having source plus q, you are having sink minus q, but one is nullifying by the other, and hence you can simply say neither source nor sink is present at this point. So at this location what you are going to get? You are going to get divergence is equal to 0. So from these three cases we have given a statement here. We have made one observation from these three cases. Let us say this is case 1 and this is case 2, and let us say this is case 3. So from these three cases we have observed one thing here. So what is that here? See, for the divergence to exist here, for the divergence to exist at any point, for the divergence to exist at any point, at that point what must be present? Either source or sink must be present. Either source or sink must be present. So if neither source nor sink is present at a point, then at that point divergence will be what? Divergence will be equal to 0, right? Okay. Okay. So sir, what is the syllabus for IN in EMT? See, the syllabus for instrumentation students and electrical students both are same here. You are having the same syllabus that is present for electrical. Okay. See, whatever may be the syllabus, now we are discussing basics here. So these basics are very much important, either you are EC, electrical or instrumentation. Okay. So these basics are very, very important, right? So you are having for instrumentation and electrical, you are having only electrostatics part and magnetostatics part here. You are having only statics part, right? You don't have electromagnetic wave propagation and transmission lines, waveguides, all those things are not present in your syllabus. Okay, so first I am dealing with the common portion that is present for EC, electrical and instrumentation, right? So everybody here, everybody, whatever may be the branch, everybody has to study these basics compulsory in order to understand the subject clearly, right? Okay. Okay, now see here. So what I am saying here, now if you consider any point here other than the source, other than the source point, you can consider any point here. So what happens here, whatever the field that is entering towards this point, the same field is leaving from this point. So at this location we can say divergence is equal to 0. And if you consider some point here, whatever the field that is entering towards this point, the same field is leaving from this point. So at this location also I can say divergence is equal to 0. So that means whatever the point you can take here, whatever the point you can take other than the location of source, at all those points you are getting what? Divergence is equal to 0. Now coming to this one, whatever the point you can take, other than the location of sink, other than the location of minus q. Okay, what you are going to get? Consider this point. So here whatever the field that is entering, the same field is leaving from this point. So at this location also divergence is equal to what? Divergence is equal to 0. So except at the location of minus q, at each and every point other than minus q location, at each and every point you are going to get divergence is equal to what? 0, right? So from all this what we can observe is for the divergence to exist here, for the divergence to exist at a point, then at that point either source or sink must be present at that point. Yes or no? For the divergence to exist at any point, then at that point there must be what? There must be either source or sink, right? Okay. Source or sink must be present at that point here. So that is very, very important. So these things we have seen in the previous session itself. Next I have given some more examples here, like if suppose the field is entering towards a point, and here the field is leaving from the point, from the point. So all the field lines are entering towards this point and all the field is leaving from this point. Now here this field is nothing but entering field and this field is nothing but leaving field. Now if you observe, I have represented the leaving field, the length of leaving field vectors I have represented with greater length when compared to here. I have represented with larger length when compared to here. So that means the leaving field here is greater when compared to what? Entering field. So that means what is the net field that is leaving from this point here? So the net field that is leaving from this point is greater than 0. Yes or no? I have explained clearly each and everything in the previous session itself. So just I am revising here. Okay. So here the net field that is leaving, is greater than what? Net field leaving is greater than 0. So that is you have to take leaving field minus entering field. You are going to get positive value, that is net field leaving is greater than 0. So that means here the divergence is what here? Divergence is greater than 0. Divergence is greater than 0. So if divergence is greater than 0 means what must be present at this location? What must be present at this point? So some source must be present. If divergence is greater than 0 means some source must be present at this location, right? Okay. Now similarly, if you consider the field, if suppose this is the entering field, so this field is entering towards this point and the field is leaving from this point, right? So this field is entering towards this point and this field is leaving, some field is leaving from this point. Now if you observe here, so this is entering field and this is leaving field, So here if you observe here, leaving field is lesser than what your entering field. So that means net field that is leaving from this point, is less than 0. So that means at this location you are going to get what? Divergence less than 0, So that means what must be present at this location here? At this location sink must be present. Yes or no? Right? Okay. Shiva Prasad, your teaching is good, sir. This is my first class. Okay, yaar, no problem. Okay, no problem. You can listen to this class. We are having previous sessions also that are available in YouTube channel. Okay. So in our Gate Academy Global channel, if you want, you can go through those lectures also. Okay. So it is going to be very much helpful here. Right. So divergence less than 0. Now if you consider the field that is entering and this is the field, let us say this is the field that is leaving here. So here this is the field that is entering and here this is the field that is leaving, right? Okay. So now here if you observe here, whatever the field that is entering, the same field is leaving here. So that means the net field that is leaving from this point is equal to 0. That means at this location divergence is equal to what? Divergence is equal to 0. So if divergence is equal to 0 means what here? At this location neither source nor sink is present. Neither source nor sink is present, right? Okay. So up to here, so these things we have seen here. Up to here we have seen in the previous sessions. Okay. So next we have seen how to represent the divergence of vector field mathematically. So divergence of f bar is equal to what here? See, this f bar is going to have what? This is vector field. It is going to have x component, y component and z component. This f bar is going to have x component, y component and z component. So if you expand this divergence of f bar, what you are going to get? What I told you here. So differentiate the x component of vector field with respect to x. This is going to be the first term. Second term is going to be differentiate the y component of the vector field with respect to y and differentiate the z component of vector field with respect to z. So this is going to give you what? This is going to give you divergence of a vector field here. So take x component of the vector field, differentiate with respect to x, take y component of the vector field and differentiate with respect to y, take z component of vector field and differentiate with respect to z. That is going to give you what? That is going to give you the divergence of the vector field, right? Okay. So we have seen that this is nothing but what here? This is nothing but a scalar quantity. So next I have told that if divergence of vector field f bar is equal to 0, if divergence of any vector field is equal to 0, then f bar is said to be what here? Then f bar is said to be what? Is said to be divergenceless. Yes or no? Then f bar is said to be divergenceless or solenoidal, right? So if you try to calculate the divergence of any vector field and if you got the divergence of that vector field is equal to 0, then we can simply say that vector field is called as what? That vector field is called as divergenceless or solenoidal, right? Okay. So based on this I have solved one problem also here. Right? Okay, so that is, I have given one problem here. I have given some vector field, right? I have given some vector field. So here I have given some unknown value, I have given some k something, k minus 1 or something I have given. Okay, I asked to determine this unknown value k, right? I have given x component and y component and z component of the vector field. So here I have given some unknown value of k. So and I ask to determine what? I ask to determine k value if f bar is what? If f bar is solenoidal. If f bar is solenoidal. Then what you have to do? Since f bar is solenoidal, what you have done? You have taken divergence of this vector field and equated equal to what? Equal to 0. So from that you have determined what? K value. Okay, so if you want, you can go through that problem here. I have already explained the problem based on this solenoidal field or divergence less, right? Okay, so up till here we have covered in the previous session. Okay, okay, yeah. So now so in today's class we will start divergence theorem here. We will study about divergence theorem. See, once you understood what do you mean by flux, how to represent flux, and what do you mean by divergence, how to represent divergence. So if you understood all these things here, then this divergence theorem is going to be very, very simple. See here. See, if suppose, okay. So now see here, I am considering a cube here. I am considering a cube, or I can say simply a closed surface, right? So I am considering a closed surface like this. Okay, so some closed surface I have considered here. I have considered some closed surface. So that closed surface here is nothing but it is just like cube. Right? Okay. So now here, so this is the side surface here. This is the side surfaces, and this is top surface, and this is bottom surface. Right? And here this is back surface, and here it is front surface. Okay, so you are having front surface, this is blue lines represents front surface, and this lines represents back surface, and here this is side surface, this is also side surface, this is bottom, this is top surface. So how many surfaces you are having here? Total 6 surfaces. Yes or no? So total you are having 6 surfaces. So let us say front surface is 1, back surface is 2, okay, and this is side surface is 3, and this is 4. Let us say this is 5, and this top surface is 6. Okay, so total you are having how many surfaces here? 6 surfaces. I have considered 6 surfaces here, right? Okay. Now let us assume okay, so let us consider some vector field is leaving this closed surface here. Let us assume some vector field is leaving this closed surface. Okay, so let us assume some vector field is leaving this closed surface like this. Let us assume. Okay, so the vector field that is leaving this closed surface is nothing but f bar here. The vector field that is leaving this closed surface is nothing but f bar. right? Okay. Okay, yeah. Now see here, so the field that is leaving any closed surface, see I cannot draw through, I cannot draw the vector field coming out of this first surface and the second surface here, okay. So front surface is present like this, back surface is present like this, okay. Okay. So I hope you have understood here. So now let us assume some vector field is leaving this closed surface here. Some vector field is leaving this closed surface. So what do you mean by the vector field leaving any closed surface here? The vector field that is leaving any closed surface, we can say it as what? We can say it as flux leaving the closed surface. Flux leaving the closed surface. See, the number of field lines that are penetrating through any surface is called as what? Is called as flux. Yes or no here? So now here the field lines are penetrating through this surface, through this surface, through this surface, through this surface, front surface, back surface. Yes or no? So this total surface will form what? A closed surface. So the number of field lines that are penetrating through this closed surface is called as what? Is called as flux leaving the closed surface. Flux leaving the closed surface. Now mathematically, how to represent the flux leaving the closed surface here? Mathematically, how to represent the flux leaving the closed surface? So I have already told here how to represent the flux leaving the closed surface. So the flux leaving the closed surface, we can represent it as what? Closed surface integral. Here the vector field, I am considering it as what? F bar, right? So you can represent it as F bar dot dA bar. So I have explained in this manner here. See, F bar dot dA bar will give you the flux through any small differential area. Now if you want the flux through the total closed surface, then you have to integrate throughout the closed surface. So this is going to give you the flux through what? The flux through closed surface here. The flux through closed surface, right? Okay. Okay. So this is going to give you the flux through closed surface. Now see here, now my question is, see, if the field is leaving this closed surface, some field is leaving this closed surface, means there must be a source of this field inside this closed surface or not? See, we are having some closed surface. So from that closed surface, field is leaving here. Some vector field is leaving that closed surface. So that means inside that closed surface, there must be a source of that field or not? There must be a source of that field. See, if there is no source, there will be no vector field. Yes or no here? See, it is just like if you are having a closed surface like this, if suppose smoke is coming out of that closed surface here. Let us assume smoke is coming out of that closed surface. Okay, then inside that closed surface, what must be present? There must be a source for that smoke. Yes or no? There must be a source for that smoke. So inside there may be some persons are sitting and they are smoking, maybe. Okay, so that is the source. Yes or no? So because of that source, we are seeing the smoke that is leaving the closed surface. Yes or no? Okay, so that means some vector field, whenever some vector field is leaving the closed surface, means inside that closed surface there must be a source that is producing this vector field. Yes or no? If there is no source, there is no field that is leaving the closed surface, right? So that means inside the closed surface, there must be what? There must be a source. There must be a source present inside the closed surface. Yes or no? Some sources must be present inside the closed surface that is causing the field, that is causing this field that is leaving the closed surface. Whatever the field that is leaving the closed surface, so that is caused by what? That is caused by the source that is enclosed by this closed surface. Yes or no here? Yes or no? Okay. So that means see here. Now here, wait here. So see here. Right. Some field is leaving this closed surface, means there must be sources. There must be sources that are present. There must be sources inside this closed surface. Yes or no? See, this closed surface is going to enclose this volume or not? Yes or no? This closed surface is enclosing this volume. So within this volume there must be some sources that are producing this field, right? Okay, so now let us assume you are having the sources distributed throughout this volume here. You are having the sources that are distributed throughout this volume, right? Let us assume you are having the sources that are distributed throughout this volume. You are having many number of sources within the volume enclosed by this closed surface. So each source is producing some vector field. Yes or no? So all these sources are producing some vector field, and the resultant vector field is leaving the closed surface, right? Okay, so I hope it is clear here. Whatever I am explaining, I hope it is clear. Yes or no here? Okay. Okay, yeah. So now see here. Now let us consider this source here. So so here this source is going to produce some field. Yes or no? So that field is going to leave from this source here. So this source is producing some field. So that field is leaving this source. And here you consider another source here. So this source is also from this source point also you are going to have the field that is leaving from this point. Yes or no? So like that, each and every source is going to produce what? Is going to produce some vector field that is leaving from that point. If I consider a source here, if I consider all this as sources, then from each and every source, there will be a field that is leaving from that source point. Yes or no? There will be a field that is leaving from that source point. Yes or no? Yeah? Yes or no? So now if I add up all the fields, that are leaving from each and every source here, then what I am going to get? Finally, I am going to get the field that is leaving this closed surface or not? Yes or no? Yeah? So whatever the field that is producing within the volume here, only that field is leaving this closed surface or not? Yes or no? Now, how I can calculate the field that is produced within this volume? What I can do? So, you are having many sources present within this volume. I have to calculate what is the field that is leaving from each and every point. Then if I add up all those, okay, I am going to get the field that is leaving the closed surface. Yes or no? And we know that the field that is leaving from a point here, is nothing but what? Is nothing but divergence. Yes or no? Here? So that means you have to calculate the divergence. At each and every point, throughout the volume here, So if you add up all those divergences, throughout the volume, you are going to get what? You are going to get the flux that is leaving the closed surface. See, divergence means what here? Divergence means what? It is a measure of what? It is a measure of how much of the field is leaving from a given point. Yes or no? Now here you are having many sources within the closed surface, that is within the volume enclosed by this closed surface. So from each and every source is going to produce some field. Yes or no? The field is going to leave from each and every source here, right? So that means if you want to measure how much of the field that is leaving from each and every point, then you have to calculate what? You have to calculate the divergence at each and every point. So if you add up all those divergences here, throughout the volume, then you are going to get the total field that is leaving the closed surface. Yes or no here? Is this clear here? Is this point clear? Yes or no? Is this point clear here? Yes? See, if this point is clear, then we will move on further here. Is this clear? I am waiting for your reply. Yes? share the session here, share the session to as many students as possible so that everybody will get benefited. Yes. So I hope it is crystal clear here. I hope it is crystal clear, right? So that means if you add up the divergences, throughout this volume here, that means you are calculating how much of the field that is leaving from each and every point throughout the volume. So if you add up all those, you are going to get what? You are going to get the field that is leaving the closed surface. Yes or no? Okay. So that means the flux that is leaving the closed surface here, is equivalent to what here? The flux that is leaving the closed surface is equivalent to what? Is equivalent to sum of the divergences throughout the volume. So at each and every point you have to calculate the divergence and you have to add up all those divergences throughout the volume. That is going to give you what? That is going to give you the total flux that is leaving the closed surface. So that means you have to add up the divergences throughout the volume. So how I can represent that mathematically here? So you have to add up all the divergences throughout the volume. So that means you have to do triple integral divergence of what? Divergence of f bar into what? Into dv. Yes or no? So you are adding up all the divergences throughout what? Throughout the volume. So this is going to give you what? This is going to give you the flux that is leaving the closed surface. Yes or no? Okay. Yes. Harry, it's clear. Okay, thank you. Okay, so the flux that is leaving any closed surface, can be represented as what here? Can be represented as triple integral divergence of f bar into dv. So this represents what? You are adding up all the divergences throughout the volume. So that means you are calculating at each and every point what is the field that is leaving from that point. So if you add up all those, you are going to get the flux that is leaving the closed surface. Right? Okay. So this is called as what? This is called as divergence theorem. So you can represent the flux leaving any closed surface in this manner, or you can represent the flux leaving the closed surface in this manner also. Right? So this is nothing but what? This is nothing but divergence theorem. So now what is the advantage? Of using this divergence theorem? See, the advantage here is the mathematical calculations here. The mathematical calculations will become very simple. The mathematical calculations will become very simple if you use what? If you use this divergence theorem. If you use this divergence theorem, the mathematical calculations will become very simple. See, for example, if you want to calculate the flux through closed surface here, that is closed surface integral f bar dot dA bar. Let us assume this cube here. Right? So this cube is having how many surfaces here? 6 surfaces. Yes or no? Front, back, sides, top and bottom. So total 6 surfaces it is having. So now in general, if you want to determine the flux through closed surface, okay, then what you have to do? You have to determine the flux through front surface. Yes or no? You have to determine the flux through front surface. Yes or no? So front surface I am naming it as, so here I have named here. So front surface is 1, back surface is 2, side surface 3, 4, 5, 6. Right? Okay. So you have to determine the flux through first surface, plus you have to determine the flux through second surface, plus and so on. You have to determine the flux through sixth surface. Right? Okay. So you have to determine the flux through first surface and second surface, third surface, fourth surface, fifth surface and then sixth surface. So if you add up all this, you are going to get the flux that is leaving this closed surface. That means how many times you have to perform this integration here? 6 times or not? Here 1, 2, 3, 4, 5, 6. Yes or no? 6 times you have to perform in order to calculate the flux through the closed surface. So instead of following this lengthy procedure, you can apply simply what? You can apply simply divergence theorem. right? So if you apply divergence theorem, you can represent this as what here? This you can represent it as triple integral divergence of f bar into what? Into dv. Right. So for the given vector field, just try to determine the divergence. So you are going to get some expression here. So if you calculate divergence of f, you are going to get some expression here. So just you have to integrate that throughout the volume. Okay, just calculate the divergence and integrate that function throughout the volume. So you are going to get what? You are going to get the flux through the closed surface. So this is a simplest procedure when compared to this one here. So this is the advantage. Of using what? Of using divergence theorem. Yes or no? Okay. Okay. Yeah. Okay. So what here? Hari sir, sorry, before I can't mention sir. What here? Before I can't mention sir. I have not understood here what you are saying. Okay. Okay. So is this clear here? Divergence theorem. The purpose of divergence theorem and why we are representing this closed surface integral in this manner. So all these things, I hope it is crystal clear. Yes or no here? Yes? Okay. Okay. So now let us take one simple problem here. Let us take some simple problem. So now let us consider let the vector field f bar is equal to, we will take some simple vector field here, that is x ax cap plus y ay cap plus z az cap. So let us consider this vector field. So let the vector field be f bar is equal to x ax cap plus y ay cap plus z az cap. Okay. So then determine the flux leaving through the closed surface. Determine the flux leaving through the closed surface defined by so x is varying from -1 to 1 and y is varying from -1 to 1 and z is varying from -1 to 1. Okay. So what they have given here? Let the vector field f bar is equal to x ax cap plus y ay cap plus z az cap. Then determine the flux leaving through the closed surface. Defined by what? Defined by x varying from -1 to 1, y varying from -1 to 1, z is also varying from -1 to 1. So that means this represents what here? This represents what? X is varying from -1 to 1, y is varying from -1 to 1, z is also varying from -1 to 1. So let us assume this as x-axis and this as y-axis and z-axis is coming out of the board. Let us assume z-axis is coming out of the board. Yes or no? So x is varying from -1 to 1 and y is varying from -1 to 1 and z is varying from -1 to 1. So with this what is the closed surface you are going to get here? You are going to get what? You are going to get cube or not? Yes or no here? You are going to get a cube, right? Okay, so if x is varying from -1 to 1, y is varying from -1 to 1, and z is varying from -1 to 1, you are going to get what? You are going to get a cube. You are going to get a cube. So now they are asking to determine the flux that is leaving the closed surface, or the flux that is leaving this cube here, this cube, right? So now see here. See, if I draw that cube here, I am roughly drawing here, okay? So just in order to get some idea, see here, okay? So let us say this is cube here. Let us say this is cube. So this is x-axis, this is y-axis, and this is z-axis, right? Okay. So this direction is x-axis. So that means this plane is nothing but what here? X is equal to constant plane or not? Yes or no? See, this plane is yz plane. This plane is yz plane. This side surface is yz plane. That means x is equal to constant plane. So this side surfaces are x is equal to constant plane. Okay. So now here this will become what? This will become x is equal to -1 plane, and this will become what? X is equal to 1 plane. Yes or no here? Okay. So here you are having x is equal to 1 plane, and here you are having x is equal to -1 plane. Here x is equal to 1, here x is equal to -1, right? So in this manner, here x is equal to -1 plane here, and x is equal to 1 plane here, right? Okay. Okay. Next here y is varying from where to where? -1 to +1. So y is varying from -1 to +1. So see here. So let us say this will become what? See, y is varying in this direction, yes or no? Y is varying in this direction, right? So this plane is nothing but y is equal to -1. So this plane will be y equal to -1, and this plane will be y is equal to +1. This plane will be y is equal to +1, right? And front surface here, so front surface is nothing but what? Z is equal to 1. Front surface is Z is equal to 1, and back surface is, this is back surface is Z is equal to -1, right? Okay. So y is equal to -1, y equal to +1, x is equal to -1, x is equal to +1, z is equal to +1, z is equal to -1. So this is the cube they have given here. This is the cube they have given, right? Okay. So now they are asking to determine the field, to determine the flux that is leaving this closed surface. So they have given the vector field f bar is equal to what? F bar is equal to x ax cap plus y ay cap plus what? Plus z az cap. So if you want to determine the flux that is leaving this closed surface, what you have to do here? How to determine? You have to do closed surface integral f bar dot what? F bar dot dA bar, right? Okay. So this is equal to what? This is equal to, so I said you have to consider what? You have to consider 6 surfaces. Yes or no here? You have to consider all the 6 surfaces. So let us consider this is 1, and this is 2, okay, and this is 3, this is 4, front surface 5, back surface 6. Let us consider all these 6 surfaces here. So what you have to do? So you have to determine the flux through what? You have to determine the flux through this first surface, plus you have to determine the flux through second surface, plus you have to determine the flux through third surface, plus you have to determine the flux through fourth surface, plus you have to determine the flux through fifth surface, plus you have to determine the flux through sixth surface here, right? So this is going to be a lengthy procedure. See, I have given a simple function here. I have given one simple function, that is x ax cap plus y ay cap z az cap, right? Okay, so instead of following this lengthy procedure, you can apply what? You can apply simply divergence theorem. You can apply simply divergence theorem. So by applying divergence theorem, this closed surface integral f bar dot dA bar, that is flux leaving any closed surface, can be represented as what here? Can be represented as triple integral divergence of what? Divergence of f bar into what? Into dV. F bar into dV. Yes or no here? So if you do this, what you are going to get? Tell me. What you are going to get? Tell me. So this is equal to. So now here the variables are x, y and z. So this dV is nothing but what? dV is nothing but dx, dy into dz. Yes or no? The integration variables are nothing but dx, dy and dz. Right. Now what is divergence of f bar here? So f bar is equal to what? F bar is equal to, they have given x ax cap plus y ay cap plus what? Plus z az cap plus z az cap. So if you calculate the divergence of this function, what you are going to get? What I said here, how to calculate the divergence? Take the x component and differentiate with respect to x, and take the y component and differentiate with respect to y. Take z component and differentiate with respect to z. So add up all this, what you are going to get? So here 1 plus 1 will be 3. Yes or no? So I can directly write triple integral divergence of f bar value is nothing but what? Is nothing but 3. So 3 into dx dy dz. Now here x is varying from where to where? X is varying from -1 to +1, y is varying from -1 to +1, z is also varying from -1 to +1. So if you do this here, what you are going to get? So 3 into x, its range is from -1 to 1, y -1 to 1, integral dz is z -1 to 1. So you are going to get 3 into, substitute this, you are going to get 2, 2, 2. Yes or no? So 2 into 2 into 2 into 3. What you are going to get? 8 into 3, that is 24 units. So some 24 units. Yes or no? So you have calculated in a simple manner or not? By using the divergence theorem, you can calculate the flux through any closed surface in this simple method. Right. See, if you use this one here, you have to determine the flux through x equal to 1. Then you have to determine flux through x is equal to -1. So in that manner, you have to determine the flux through what? The flux through all the 6 surfaces. Okay. So if you want, you can perform this operation also. And finally, you are going to get what? You are going to get the same answer, 24 units. Okay. Okay, yeah. See, I will do this one for you. So in a very simple manner, see here, closed surface integral f bar dot dA bar is equal to. Now see here, see. So take this first surface here. Let us take this first surface. I have taken a simple function here. So the calculation is going to be very simple. See here. So I have taken this first surface. So the first surface is what? X is equal to -1. So x is equal to -1 here, right? Okay. So x is equal to -1 means it is x is equal to constant plane. So x is equal to constant plane means what are variables here? Y and z are variables. Right? Okay. So now take this one here. So I am taking this first surface here, right? So I am taking this first surface here. So f bar dot dA bar. So this one, okay, first one. So this surface I am considering, that is x is equal to -1. So the variables are nothing but y and z. So that means you have to, this dA will become what? This dA will become dy into dz. So what is the direction of this surface here? What I have told here, if you are having a closed surface here, then the direction of that closed surface is always given by what? Is always given by outward unit normal drawn to that closed surface. Yes or no? If you are having a closed surface, the direction of the closed surface is always given by what? Outward unit normal. Now if you consider this surface here, If you consider this x is equal to -1 surface, what is the direction? What is its direction? Its direction is given by outward unit normal. So if you draw the unit normal in this direction, outward unit normal, so it is going to point in which direction? This is x direction, yes or no? This is x direction. So this is going to be what? This is going to be minus ax cap direction. That means this plane direction is along which direction here? Minus ax cap. Right. So that means you have to write here this dA bar. This dA bar is nothing but dy dz, and its direction is what? Its direction is minus ax cap. Minus ax cap. Okay. Is this clear here? Yes or no? Yes. See, Harry, see, if you are considering closed surface here, if you are considering closed surface, that closed surface is enclosing what? That closed surface is enclosing the volume. Yes or no? Closed surface will act as a boundary to that volume here, to that volume or to that region. So you have to note the difference between the closed surface and volume. Right. So closed surface is always enclosing some volume here. Whatever the region you are specifying, okay, that region is bounded by a closed surface. Closed surface will always bounds. Closed surface will always encloses volume here. Yes. No, you should not say flux leaving any closed volume. No, you should not say closed volume here. You have to say closed surface. Right. Closed surface means it is the boundary for that volume. Hope you have understood here. Hope you have understood. Yes. Okay. Okay. So coming to this problem, see here. Here you are having dy dz minus ax cap. So substitute here. So f bar dot, here the surface is dy dz minus ax cap. Right. Okay. So now this f bar is going to have which components? X component, y component and z component. So in the previous session I have told that, only which component will contribute for the flux here? Only the component that is along the direction of what? Along the direction of x. So that means only x component is going to contribute for flux here. Yes or no? See, if you do fx ax cap plus fy ay cap plus fz az cap dot dy dz minus ax cap, what you are going to get? Ax cap dot ax cap will become 1, ay cap dot ax cap will become 0, az cap dot ax cap will also become 0. So what is the only component left out? That is only fx. Yes or no? So just write down that here. What you are going to get? You are going to get double integral. Here the variables are y and z. So y is varying from -1 to +1. Z is varying from -1 to +1. And x component is nothing but what? X component is nothing but x. Yes or no? That's what we have given or not? We have given f bar is equal to x ax cap. F bar is equal to x ax cap plus y ay cap plus z az cap. So here x component is nothing but what? X. Yes or no? So you can just simply write x dy dz, x dy dz. Here you are having, see, x ax cap. This is, if I consider only x component, you are having only x ax cap. So if you do the dot product, what you are going to get? X into dy dz, ax cap dot minus ax cap will become -1. Yes or no? So you are going to get here -1 here. So this is the expression you are going to get. Now if you do this one here, what you are going to get? So this is for which plane here? Which surface this is for x is equal to -1 surface or not? We have considered the first surface is nothing but what? X is equal to -1 surface. Yes or no? Okay. So this is for x is equal to -1 surface. X is equal to -1 surface. This one. Right. Okay. So now see here. What you are going to get here? Tell me what you are going to get. So x is constant with respect to this integration variables. So take it out of the integration. You are going to get minus x. So integral dy is y. Its range is from -1 to 1. Integral dz is z. Its range is from -1 to 1. So here x value is equal to what? This represents what? This is nothing but x is equal to -1 surface. X is equal to -1 surface. So just substitute x is equal to -1 here. So minus of -1 will become what? Will become +1, right? So into here you will get 2 and here you will get 2. So that means you are going to get what? You are going to get 4. Right. Now, if you consider the second surface here, if you consider the second surface, what you are going to get? What you are going to get? Here f bar dot dA bar, f bar dot dA bar. Now here the second surface is nothing but what here? Second surface is nothing but what? X is equal to 1 surface. So what is the direction of this surface? The direction of this surface is given by the normal, the unit normal drawn to this surface. So if you draw the outward unit normal to this surface, it is going to point in which direction? Ax cap direction. Right. So I can represent, so the flux through this x is equal to 1 surface, flux through x is equal to 1 surface. So I am considering x is equal to 1 surface here, x is equal to 1 surface. So this is x is equal to constant surface. So that means dA is nothing but what here? What are variables? X is equal to constant means y and z are variables. So you can represent this as what? Dy dz. But what is the direction of this surface? Always the direction of the surface is given by what? Outward unit normal. Yes or no? Outward unit normal. So that is in which direction? Ax cap direction. Right. Now here f bar is having x component, y component and z component. So which component will contribute? Which component will contribute? Only x component will contribute. And x component is nothing but what? Simply x or not? Yes or no here? So here you are going to get what? You are going to get double integral here x dy dz. You are going to get x into dy dz. Yes or no here? Yes or no? X component is x here. Yes or no? So x ax cap dot dy dz ax cap. You are going to get what? X into dy into dz. See, if you observe here, and here y is varying from where to where? Y is varying from -1 to +1 and z is varying from where to where? -1 to +1. Z is varying from -1 to +1. Okay. If you observe here, what you are going to get here? What you are going to get? X is constant with respect to integration and x value is equal to what? X value is equal to 1. This is the second surface. Yes or no? So take it out of the integration. So you are going to get x. Integral dy is y, integral dz is z, its range is from -1 to 1, -1 to 1 and x value is equal to 1. So what you are going to get? You are going to get here 1, here you are going to get 2, here you are going to get 2. So this is equal to 4. So in the same manner here, if you calculate for other surfaces also. See, for this surface we got the flux through this surface we got 4. Yes or no? The flux through this surface also we got 4. Similarly, if you calculate the flux through front surface, back surface, top surface and bottom surface, through each and every surface you are going to get what? You are going to get the value 4 here. You are going to get the value 4. So if you want you can check. If you want you can check. Okay. If you want you can check here. So everywhere you are going to get what? The flux through front surface is 4, the flux through back surface will also be 4, the flux through side this side surface is also 4, this also 4, this is also 4, this is also 4. So what is the total flux you are going to get? If you add up all those here, finally you are going to get what? You are going to get the closed surface integral f bar dot dA bar, that is the flux through the closed surface. You are going to get what? If you add up all the fluxes through all the 6 surfaces, finally you are going to get 24 units only here. Finally you are going to get 24 units only. So that means here whatever the procedure you are following here, okay, whether you can follow this procedure, that is you can add up the fluxes, through each and every surface. That means you can follow this procedure, or else you can apply simply divergence theorem. So which method is simpler here? Which method is simpler? See, if you do the integration here, you have to do the integration 6 times here, which is very lengthy. Yes or no? Whereas if you solve the same problem with the help of what? With the help of divergence theorem, so you get within 1 or 2 steps you got the answer. Understood? So that's why we will use what? We will use divergence theorem here. So by using divergence theorem, this mathematical calculations will get what? Will get very much simplified. This mathematical calculations will get very much simplified. So that is the advantage of using this divergence theorem here. Yes. Understood here? Is it clear? Yes or no here? Is it clear? So finally, the divergence theorem we got as what? The flux that is leaving any closed surface can be written as what? Is equivalent to triple integral divergence of f bar into dv. Okay, so this is divergence theorem. This is divergence theorem. So the purpose of divergence theorem is the mathematical calculations will get very much simplified by using the divergence theorem here, right? Okay. So is this clear here? Is this divergence theorem clear, everybody? Yes. Okay. Hari, yes sir. Okay. Yeah. So next we will study about circulation of the vector field, circulation of the vector field around any closed loop. Okay, we will study this one. So once we complete this one, next we will go for curl here. Next we will go for curl, right? Okay. Once we complete curl, next we will go for Stokes theorem. So once we complete Stokes theorem, then we will go for null identities here. So these are the topics that we have to cover here, So with this here, once we complete all these topics, then we will complete the basic mathematics part that is needed to understand this subject here. Okay. So from the next session onwards we are going to study these topics here, So that is, in the next session I am going to start circulation of the vector field, around any closed loop, and we will cover curl, and also we will cover Stokes theorem here. Okay. So after this we will cover null identities. So once we complete this, then we will enter into statics part, that is electrostatics, right? Okay. So is this clear here up till now? Yes. Okay here. So I am winding up the session here with this. So tomorrow I will start circulation and curl here. Okay. So today I am winding up the session with this, right? Okay. Is there any doubts here? If you are having any doubts, please post it in comment box here. Please post it in chat box if you are having any doubts. If you are having any doubts, please post it in chat box. We will discuss. Otherwise, I will wind up the session. Let me know is everything is clear. Yes or no here? Okay. Okay, yeah. So I hope it is clear. So no, I think nobody is having any doubts. Okay. Okay then. So I am winding up the session here with this. So tomorrow we will start circulation and then curl and then Stokes theorem here. Right. Okay. So tomorrow exactly same time here. Tomorrow exactly at 4 p.m. Daily EMT lectures will be there exactly at 4 p.m. Right. So daily the class will start at 4 p.m. So share the session here, share the session to your friends, share it to maximum number of students here, so that everybody will get benefited, right? Okay. Okay here. Okay. So with this I am winding up the session here. Okay then, thank you, bye bye.